Well, good morning, everybody, and we are very honored to have you here today. I would like to begin by first and foremost thanking the Cancer Research Institute for their support of these summits. There are a number of them that are going on around the country, and we are thrilled to be able to have you all here in the conference in the Northeast. These, I think, are very unique in that we're going to give you today an update on the state of the art of what is an area that is transforming the care of cancer patients today, the use of our body's immune system to fight cancer. And you'll hear a lot of experts and information, but I think more importantly and invaluable will be the perspective that's integrated into this conference from our patients and their caregivers to give you their direct experience, what it's been like for them, and the types of things they've experienced, in the hope that you will be inspired and more hopeful and encouraged and confident in thinking about really what's become an explosion of information that's out there, almost overwhelming. But to get this kind of information and feedback and organized in this conference, I hope will give you all some perspective of how to think about that enormous amount of growing information and how it may help you and integrate into your journey for your cancer. A couple of quick logistical issues. We're trying to navigate the temperature here with everybody in the room. We worry it may start to get a little too warm, but if it's too cold, I see a lot of people wrapped up and in sweaters. So if it's too cold, we'll do our best to adjust the temperature, try to keep it not too chilly. Bathrooms are, if you go by the elevator and just down the hall a little bit, they're off to the right. Down there, there's water and coffee off to the sides. And we will be having lunch in a little bit here. So my job this morning is to make you all immunology experts and share with you a little bit of information about this very exciting topic and field. So let's move ahead. The first slide, what I'm going to do over the next 20 to 25 minutes is give you a little background about immunology and immunotherapy. Dr. Glimcher gave us really a terrific perspective on how things have moved to where they are. I think we're still scratching the surface and just hitting the tip of the iceberg. We've got a long way to go, but it's been a remarkably exciting past few years. I want to give you some basics about how our immune system works. I try to bring this forward in a way that there's a tremendous amount of complexity here in the system that Mother Nature provides to us and designed for us to protect us from anything that's foreign or potentially harmful. But I'm going to try to bring that complexity into a level, I can't talk about everything obviously, but important aspects of it and how that is evolved and integrated into different aspects of treatment for cancer. And there's four main areas I want to briefly touch on and highlight. First of all, the immune checkpoint therapies that Dr. Glimcher mentioned. Those are the ones that are most prominent and are out. You'll see them on TV, advertisements in the New York Times and newspapers and magazines. They've had the biggest impact so far, but there's also a lot of exciting work on other areas of strategies to tap into the potential of the immune system. One area called adoptive cellular therapies and chimeric antigen receptor therapies, or CAR therapies. We're going to talk about those in a little bit, and they have literally transformed how we treat hematologic malignancies, leukemias and lymphomas, giving us a treatment option for patients who had nothing left, been through the whole gamut of bone marrow transplant and extensive chemotherapy, who now are effectively cured with this strategy to tap into the potential of the immune system. I want to talk about briefly a very exciting area you may hear about or have heard about in the news of oncolytic viruses, where viruses are genetically engineered to help us attack cancer cells, and then talk a little bit about vaccines. And then I'm going to wrap up with some of the challenges and why this isn't working, our understanding of why these approaches aren't working for everybody, but what we're learning and hoping to be able to overcome some of those hurdles and challenges. So the idea of trying to tap into the potential of our immune system to fight cancer is not a new idea. This has been around for a long time. And one of our heroes for those of us in the field, as Dr. Glimcher mentioned, is Dr. William Coley, this sarcoma surgeon from New York who, as she mentioned many years ago, made this astute observation that infections can help patients live longer from their cancer. And nobody understood anything about the immune system then, or even that we really had it. But it was just an astute observation. And back then, there was nothing to offer patients for their cancer. And surgeons, that was all they could do, was operate on the tumor. And the critical thing for a surgeon at that time was to be able to do that surgery safely and effectively and not have an infection. That was the benchmark of how they were successful, because if they got through, the patient got through and didn't have any complication, that was a good surgery, and the best surgeons had the best rates of not having those complications. So you can imagine the situation of Dr. Coley when he made this observation and said, well, my patients are living longer. I'm going to try to take advantage of this. And he started inducing infections in his patients postoperatively, and everybody ridiculed him back then. But his patients lived longer. And that was the birth and what gave rise to tapping into the discoveries made of our natural defense system, the immune system, to fight infection. Dr. Paul Ehrlich was one of the pioneers who began to dissect the different cells in the immune system and how they may work together and complement each other. And then Lloyd Old is recognized as one of the modern era cancer immunology forefathers, if you will, who made a lot of the discoveries about how the immune system and cancers interact and how we can tap into that potential. So this idea and strategy has been around for a while. So why are we interested in this? Why do we think the immune system could work or make a difference here? And our immune system is a remarkable system in our body to help protect us from anything that's foreign or potentially harmful. And it has many different attributes or functions. And I'm going to highlight 3 of them that we think are critical in helping fight cancer. First of all, the immune system is capable of a very potent, robust, coordinated attack against something that's harmful or foreign. And if you think about it, a cancer is something harmful and foreign, and immune system should want to recognize and attack it. What I've got up here, not sure if I've got a mouse up here or not to help, but that's okay. I can highlight up on the graphic here. This is a patient where you can see a large, you guys can still hear me. Yeah, you can see a big nodule of melanoma cancer under the skin, on the skin in this patient. This patient on the CAT scan or the CT scan underneath here, this white area is the area of cancer of the CT scan there. And after 1 dose of immunotherapy treatment, 6 weeks later, that mass, that cancer, that lump, about the size of a peach or a plum, maybe a little bigger, cells, the microscopic cells from the immune system mobilized, attacked that peach or plum, and it vanished, it disappeared. And you don't see it on the CAT scan there. So that's one example of when it's working well, how robust and remarkable it can be. The other attribute of the immune system to highlight is it is exquisitely specific. I like the analogy of our immune system when it's attacking a specific target. It's like an assassin. It's not a shotgun. It's not going to go out and attack or scatter around and have a lot of collateral damage. It's an assassin with one of those big high-powered rifles that's going to zoom right in and attack just that one target. Nothing else ideally in the periphery is damaged. And that's the reason the specificity is there is because we want the immune system to be able to hit the target, but we don't want it to harm or damage anything normally in our body. And as we'll talk about some of the side effects when we use immunotherapy drugs and we push them beyond the balance that Mother Nature normally designed, there can be some cross-reactivity and some side effects associated with these treatments if they're starting to harm or damage normal parts of the body. The third attribute of the immune system is that the immune system remembers. And unlike other treatments that we give and they disappear from our body, if we have a treatment that can persist, it could potentially help a cancer from recurring. So the memory of the immune system, once it's sensitized properly, it stays imprinted in the immune system in our body for years, decades to come. And theoretically, if 5 years, 10 years later, a tumor is trying to come back and the immune system had been properly sensitized, the immune system can activate again and attack that recurrence before it has a chance to come and become a recurrence or a prominent another tumor. And an example, just to highlight the memory capability of our immune system, was this case study done. The Faroe Islands are beautiful islands off the coast, teeny little islands off the coast of Iceland, a very secluded, small little communities there. And in 1781, there was a devastating measles outbreak that happened on the island. And 65 years later, a second measles outbreak occurred. And the dramatic observation was made: the people who survived the first outbreak and lived, none of them got infected with a second outbreak. So their immune system from the first exposure was able to activate and protect them when they were exposed to the measles virus again. So the high potency, specificity, and this ability to remember are really the key attributes, I think, of why the immune system, why we're excited about it as a potential cure or as a potential durable therapy for cancer patients. And this is a dream, this is an envision and that many of us have had, and fortunately is beginning to come more to a reality, but we still have a long way to go. So when we think about cancer therapies and how they work, how we measure their benefit, this is the typical way me and my colleagues think about a drug that may be working. We have a graph like this, and this is called a Kaplanmeier curve. And on the y-axis, going up and down, is the percentage of patients who are alive. And at the beginning of the, when all the patients are enrolled, here we see everybody's alive. But then over time, as you can see on the x-axis, patients are dying off. And eventually, the curve comes down and there are not surviving patients. So when we have a therapy that we're testing and we see that it's working, what we want to see, or what we have historically wanted to see to define success, is that we can shift that curve to the right. So the blue line now indicates that at any of those given time points, if you drop down at 1 year and 2 year and you compare to the red line, you're seeing a higher percentage of patients who are alive. And that's a good thing. That means the drug is working and helping a higher percentage of patients live. But what we really want to do is we want to also impact at the bottom of that curve, and those patients at the end, we want to shift that up. So we want a percentage of patients who are not only living at year 1 and year 2, but who are living at 5 years and 10 years. And that's what we refer to as the tail of the curve, where we want to see a treatment that's able to improve the long-term surviving patients, ultimately cured patients. That, to me, is what we really need to be achieving with therapies. And fortunately, that's what we have seen to some degree with some of the immunotherapy drugs. But as indicated here, there's a lot of room for improvement. We still have a long way to go. So this is our immune system at a glance. I think of this as, again, our natural defense system, and you can see the different components of it that are outlined anatomically for our body. It starts right at the beginning with our nose and mouth, where there are important structures within there to help, and throughout our intestinal tract, actually, our immune system be able to function effectively and protect us. There is a network of lymph nodes throughout our body that I think of, if you will, as bases, like a defense system, where bases for the immune system are located in these lymph nodes. And there are lots of the immune cells are growing and dividing and existing there. And then there are specialized areas where immune cells are developed and proliferate, like the thymus and the spleen, organs that are really designed for our immune system to grow and to develop effectively. And all of this, as you can see, is interconnected. Now, the army of our immune system is made up of a variety of different cells, and the main components of the army are depicted here with all of these different cell types. And this is part of that complex, sophisticated system that I mentioned, and we don't have time to get into and to talk about in detail, but I just wanted you to understand and appreciate there are many different components to the army, and each one has a specific role, and each one tends to work together. And we're going to focus and highlight on the dendritic cells and the T cells as two of the most, what we understand to be two of the most important aspects of this army to help us attack cancers in particular. So how do cancers, how does our immune system, how does this army attack cancers? Well, let's start off with what we refer to as the adaptive immune response, meaning that when the immune system is exposed to a target, it adapts and it responds against that target. So first of all, intuitively, you'd think, well, if you have a cancer, why can't the immune system cells just go there and attack it directly? And they do to some degree. These dendritic cells can go in and they can literally engulf the cancer cell and digest and attack it. That's just not feasible in order to eradicate cancers made up of billions and billions of cells, to have each immune cell be able to effectively eliminate that. So the immune system needs a way of amplifying and augmenting its ability to attack the cancer cells. So what it is able to do, when cancer cells are dying or they're attacked by an immune cell, these cancer cells break down. And as they break down, there are little fragments of those cells, dead and dying cells, that the immune system can attach to and bring into the tumor, the immune cells. Those fragments of the dead and dying tumor cells are called antigens. The immune system can grab onto these dendritic cells that are circulating through our body, and then they will collect those, and then they will bring them to the lymph nodes, to those bases of the immune cells where they're located throughout our body. They'll literally transport them to those cells and deliver them through a very sophisticated, specific binding complex called the MHC complex. And in the lymph nodes, they will react with specific T cells, and the tumor target will be presented to those T cells. And this very specific target will activate a specific T cell. And once that T cell is exposed to that target and it interacts, it's then sensitized. It's then activated. And that activated T cell is then moves out from the lymph node, from that base where it's been stationed, and goes on patrol. And it circulates throughout our body. And once it's activated and sensitized, it's on patrol, and it's hunting for anything that has that target that it's sensitized to. It won't react against anything else, but if it finds something that has the target, it attacks it and goes after it. And this is the little cartoon that shows when that target is expressed on other cancer cells, it can bind to that target on the cancer cell and eliminate the cancer cell. That's what the activated killer T cells are capable of doing for us. There are many examples in cancer where cancers take something that's normal and physiologic and protective in our body and utilize it, upregulate it, and dysregulate it in a way that gives the cancer cells an advantage. There are many different types of examples how cancer cells, that's how they can thrive and succeed in the body. They can adapt and utilize things that we normally have that help us, that the cancer cells can exploit to protect themselves. And one of the examples of something they do that's normally present in our body is that they can upregulate molecules that are normally in our body to help prevent the immune system from overactivating it. So if you think about it, when you get an infection, or you get sick, your immune system activates. Something has to tell the immune system, okay, enough, you're done, and turns it off. So there are these checkpoints of the immune system that are normally physiologically present that tell the immune system it's time to turn off, it's time to slow down, in order to provide a balance and prevent the immune system from activating and damaging normal structures as it's trying to fight that infection. And some of those molecules that the body normally uses to turn the immune system back down, kind of like a thermostat, raising and lowering the temperature, these molecules are turning the temperature back down once the immune system has done its job, are called checkpoint molecules. And some of the most important ones that we've learned about are programmed Death1, PD1, and its binding partner, PDL1. And these are molecules that cancers can upregulate. So instead of normally dialing down the immune system, the cancer is upregulating them, and they're using it to their advantage to turn the immune system off. So they're hijacking this system to deactivate the immune system. And that's what happens here. When PD1 or PDL1 are upregulated within the cancer, these activated T cells are effectively turned off. They're shut down. They're no longer able to kill the cancer cell and do their job. With that discovery, Jim Allison discovered a different molecule called CTLA-4. Gordon Freeman and others, Gordon from here, identified PD1 and PDL1 as this exploited strategy by cancers to prevent the immune system from attacking them. Once that discovery was made that that's what cancers are doing, then some cancer immunologists, smart people, said, well, why don't we just block that and see if we can interfere with that, then maybe the immune system will be able to get back on track and attack the cancer effectively. And that's where these blocking inhibitors, these checkpoint inhibitors, were discovered and utilized in the lab and now have moved into the clinic to revolutionize cancer treatment. And the purple graphic here are those molecules that block this interaction between the PD1 and PDL1 in the cancer and prevent those immune cells from being deactivated. So now they can do their job, and they can effectively eliminate and kill the cancer cell once this protective strategy by the cancer cells is overcome and blocked. So that's the background of immune checkpoint inhibitors, and there are many of them that are out there. There's, gosh, I'm trying to remember how many are currently approved, Brian? 7 are currently approved for, last I tabulated, it's somewhere, I want to say 12 or 13 different types of cancers. Many of them, of these are really having an impact across many different types of cancers. And we'll talk a little bit more about what we need to do to help those work even better. But that's the immune checkpoint story of that aspect of immunotherapy. I want to shift and talk about a second aspect of immunotherapy, and this is called adoptive T-cell therapies. And the idea here is if we understand these immune cells can effectively attack the cancer, can we take them from the patient, grow them up and expand them in the laboratory, and then give them back to the patient as a strong augmentation of that capability to fight the tumor. And adoptive T-cell therapy has been a strategy that's been around for quite a while, trying to take advantage of these cells that are sensitized in our immune system and on patrol in the body, taking those out, and then in the laboratory, growing them up, expanding them, and then giving back an infusion of thousands of these cells back to patient to try to attack the tumor. And that has been done. That's being tested and tried in a number of different types of cancers. As intuitive and simplistic as it sounds, it's very difficult to actually identify and expand these cells effectively. But it is an area of very active ongoing research. And this is one diagrammatic of melanoma where this type of approach has had the biggest impact for patients. But an adaptation of this is called chimeric antigen receptor, or CAR therapy. And this is along the same lines, but a twist on this. And here, the T cells, the immune cells, are harvested from the patient just by a blood draw from the patient. And they go to the laboratory, and those T cells are genetically engineered to express an antibody or another molecule that very specifically will react with a target that's present on the cancer cells. So for these CAR T cells to work, we have to know the target we're going after. And then that target can be engineered to be focused on by the T cells in the laboratory that are collected from a specific individual or patient. Those engineered T cells are then given back to the patient just as a simple transfusion. It's not anything more than that. These chimeric antigen receptor T cells have the little yellow graphic here, which is what's going to interact and bind specifically to the cancer cells. And here you can see they bind, this binds to the cancer cell, and upon binding, that T cell is activated T cell is able to do its job and effectively kill the cancer cells. This has some advantages that it can allow the cancer cells, T cells to attack very specifically. But we can engineer them to attack exactly what we want them to attack. We don't have to rely on that specific interaction developing and evolving between the immune system and the cancer cell. So CAR T cells have been a dramatic impact for primarily leukemias and lymphomas. The third type of immunotherapy I want to highlight is another area that we're very excited about, but it's been around for a long time, I want to say at least 20 years, where we've recognized that viruses that we get sick from have the potential to damage and harm cancer cells. So they can harm normal cells in our body, but if we can utilize them properly, they could potentially be a very potent weapon to attack cancer cells. And some of these viruses have been around and tested for 20 years ago when all of this started. We were thinking we could introduce the virus to try to kill the cancer cells, and the virus would do all of the work and kill all the cancer. And that was the naive approach we had with these engineered viruses to kill cancer cells. And actually, in thinking about it from that strategy, this type of approach worked to a little limited degree, but not very extensively. And subsequently, we've learned what really happens when these treatments are given is that the virus can attack the cancer cell, but as the virus kills the cancer cell and the cancer cell breaks down and those little fragments of the cancer cell are released, that's a very potent strategy for sensitizing and activating the immune system, because those dead and dying cancer cells can then attract in the immune cells, and they can augment that amplified response that I showed you about, where the dendritic cells and the T cells can interact. So the virus is just the first step. Now we understand the real work of this type of an approach is the immune response that's generated, kind of like the cavalry coming in to effectively attack the cancer once the initial assault with the virus has been done. And the next generation of these genetically engineered viruses are being tested in clinical trials now, where they're not only being given and the hope that they'll stimulate a very strong immune response, but the virus itself is genetically engineered in the laboratory to actually add additional molecules to stimulate even further that immune response, to activate it and stimulate it even further. So there are a number of very exciting clinical trials where we're trying to use these viruses to drive that immune response against the tumor even more dramatically. The last thing I want to focus on or talk about are vaccines. Vaccines you're all familiar with. I hope most of you have gotten a flu shot on an annual basis, so you know the principle, and you've had tetanus shots and those types of things, where the vaccine is designed to sensitize your immune system against a target to protect you from getting sick from that target. Here the idea is to take the same principle but sensitize your immune system against specific targets of the cancer cells. So the idea here is to take those broken down products of the cancer cells, these antigens that are unique to the cancer cells, put them together and generate a vaccine and administer it to patients as a strategy to provide an initial stimulus of the immune system against the cancer, and then those immune systems will mobilize, proliferate, and start this kind of domino effect that will then attack the cancer. And this is the graphic of that strategy. These little red triangles are the tumor fragments or the tumor targets that the vaccine is incorporated and administered to the patients, typically just like a flu shot, given to a patient that way. And then those targets are incorporated into the immune response. The dendritic cells work their way to the lymph nodes, stimulate the T cells that then proliferate and activate against that target, and those activated T cells from the vaccine can then patrol through the body and track down their target and kill the cancer cell that expresses the target they're sensitized against. So there are many different strategies of vaccines that are out there, trying different components to find the most robust, the strongest way to stimulate that sensitization of the immune response. We have a platform here where we take advantage of the technology that allows us to analyze the genetic blueprint of every patient's cancer, because cancers, whether it's a lung cancer or a colon cancer or a breast cancer, even though they share many features, just like us as people, we share many features. When you look at the genetic blueprint of the cancer cells, every one of them is different, just like all of us. So we now have the capability of being able to evaluate that genetic blueprint at using the state-of-the-art technology that's out there and identify what's unique and different about each patient's cancer. Try to identify the unique and different factors for each individual patient that we predict are going to be most likely to stimulate the immune system the strongest, and then build those factors into the vaccine and give that specific vaccine to our patients on an individualized, personalized, what we think will work best for them, rather than a one-size-fits-all, kind of like the flu shot or a tetanus shot where everybody gets the same thing. Here it's actually unique and personalized based on each patient's individualized tumor. Okay, so that's the overview of the different types of immunotherapy that are out there, the checkpoint inhibitors that we've talked about, the T-cell therapies like CAR T-cells, the viruses that are engineered, and then the vaccine strategies. So with all of these advances and the knowledge we've gained, why aren't we curing everybody? And unfortunately, cancers are very devious, and they have many different strategies in place to try to overcome what we throw at them, whether it be radiation or chemotherapy or biologic-based therapies or blocking their blood supply, or more recently immunotherapies. They already have intrinsic capabilities to protect themselves and block these treatments from working effectively. So right now, for most cancers, it's a subset of patients, not a majority, but a subset who are benefiting. And part of the work and research is trying to identify what are the predictors for within a given type of cancer, or which patients most likely to benefit, so we can really funnel these therapies to those patients who are most likely to benefit. And similarly, on the other side of the coin, identify the factors that predict patients who are less likely to respond and think about other options that may be better suited for them. But at the same time, trying to understand the difference, so that maybe if we better understand why it works for some and not others, we may be able to move forward and expand the capability of working for a broader percentage of patients. This is a really exciting time because we've talked about these different types of immunotherapy. If you think about it, we could put them together and they should actually add to one another and make an even stronger effect against the cancer. So a lot of the ongoing trials and research, the second and third generation trials, are putting combinations together to see if we can add or complement and get an even bigger bang for a buck against the tumor. And then, as I mentioned, one of the problems or issues is our immune system it has all of these great attributes, but it's a delicate balance. And we are disturbing that balance by trying to push it to fight the cancer effectively. And in doing that, there may be some side effects or issues. And better understanding those side effects and issues and how we can either prevent them or treat them effectively is a big area and challenge ongoing research. So why have responses been not as robust and prevalent as we'd like? Why are they relatively modest? And why are some cancers, most of my brain cancer patients and other types of cancers, unfortunately aren't responding? So some cancers are outright refractory. And why are we not seeing greater, more effective responses? And this comes back to, I think, the point I made at the beginning, where I think we're still scratching the surface and have a long way to go. But a lot of research now is understanding what these mechanisms of protection cancers have to prevent the immune system from effectively attacking them. And there are three main components here. Cancers can upregulate many molecules to give themselves a protective advantage against the immune system. We talked about PD-1 and PD-L1. That's one example. On this cartoon, every one of those little red arrows between an immune cell and the cancer cell is an inhibitory molecule. So there are many of these different molecules that cancers can upregulate, and we're going to need to overcome them to give the immune system more of a chance. Cancer cells can be like factories, and they secrete lots of different molecules, and some of these molecules are specifically secreted to inactivate or turn the immune system off. In brain cancer that I treat, there's at least 16 different molecules that these cancer cells produce that specifically can turn off an immune cell and prevent it from activating. So that's another protective strategy we need to learn about and overcome. And finally, remarkably, cancers can stimulate an influx of protective cells to prevent the immune system from activating. So let me just walk you through. This is a multiplex immunofluorescence picture of a brain tumor. And all of the blue cells in the background are brain tumor cells. The immune cells that are in there trying to fight the cancers are the little red ones. You can see a couple of them there. There's not many. And then there's all these yellow cells that are in there. All those yellow dots are cells. And those yellow cells are not normally there in the brain. Those are cells that the cancer has recruited from the body into the brain to protect and turn off, to protect the cancer and to turn the immune system off. These are called macrophages or myeloid-derived cells. And you can see there's an army of them there. So these immune cells that can make their way in to try to fight the tumor still have a battle to overcome in that microenvironment of the tumor because of this strategy as well, where the tumor has mobilized cells, programmed them to protect itself against the cancer. So that's the background of immunotherapy to set the stage for the rest of the day here today. We've got a very exciting program. I've given you a little background about the history of immunotherapy and why we're excited about it. You're now all experts on how our immune system can work to fight tumor. We've got these very potent weapons, the immune checkpoint inhibitors, the cellular therapies, the viruses, the vaccines. We're going to talk about some of the challenges as well and some of that work that's ongoing. So once again, thank you so much for all coming out today. We hope you enjoy the day and look forward to the next steps of the program. Okay. Okay, so at this point, we have a panel of research experts that we're going to have come up and have a discussion, and there will be an opportunity during this for your questions and input as well, and then we'll then have a patient perspective as well. Okay, so if I could, let me invite my colleagues up here. Dr. Suzanne Baumeister is going to join us up here on the panel. She is a pediatric oncologist, a children's cancer specialist here at Boston Children's Hospital. Suzanne, if you wouldn't mind coming up. Justin Gaynor is here, and Justin is a specialist in lung and thoracic cancers from Massachusetts General Hospital. And finally, Kimmy Ng is one of our gastroenterology and colon cancer specialists here from the Dana-Farber, and she's going to be representative on our panel covering that perspective.